Alright, welcome to Chapter 3. So Chapter 3 is all about two-variable statistics. So today we're going to look at scatterplots and correlations. So, scatterplot. Scatterplot is made up of a series of dots, usually on two-variable axes. So we have the independent variable and the dependent variable, and the plots are points that correspond to locations on both axes. So two-variable statistics provide methods for detecting relationships between the variables and for detecting mathematical models in their relationship. So we'll look at visual patterns in the scatterplots to reveal a relationship between the two variables. Remember, one variable is independent variable and the other is dependent variable. So independent variable is usually time or something that's not really able to change, whereas the dependent is something that changes with time, or whatever the independent variable is affects the change in the other. Okay, so the variables have a linear correlation if changes in one variable tend to be proportional to the changes in the other. So basically, the independent variable causes some sort of change in the dependent variable. Here's a bunch of positive correlations. So we have a perfect positive, which means that the scatterplot plots points line up in a nice line. We have a strong positive, so you can see the line, but it's not quite perfect. Moderate means it's scattered around. Weak, it's very scattered, but there's still sort of a defined direction, or there's no correlation. And we can do the same thing with the negative linear correlations. So in this case, as x increases, y decreases. So it goes down to the right. And you can also have the same qualifications of perfect, strong, weak, moderate, or no correlation. Don't write this formula down. I'm just showing you this so you appreciate the calculations that the computer or calculator does for you. We use this formula to find the correlation coefficient, which is R. R gives the number of measures in strength and correlation to respond to the strong, moderate, or weak. So closer the data points are to the line of best fit, the stronger the R value is, and the closer the R value is to 1 or negative 1. Okay. We could do the formula, we just have to do it in steps, but we won't really go there. Okay. So the formula for R is this. If you notice, we get to use the x squared and the sum of x. We don't really worry too much about it because we're not actually going to use it. Just appreciate that you don't have to use it. Okay. So what that does is it comes out to a number somewhere on the scale between 1 and negative 1, being negative perfect and positive perfect. Okay, so weak is 0 to a third, or 0.33, or negative 0.33. Moderate is from 0.33 to 0.67, or the negative side. And strong is 0.67 to 1, and as well on the negative side. So remember that most data points x, y used in calculating the correlation coefficient are more accurate than the model. So the more data we have, better the model. Before computers were mainstream, all the calculations were performed manually by hand, so now you can appreciate having those computers to do the calculations for you. Hence computers, computation, blah blah blah. Correlation can tell you how closely the points cluster around the line of best fit. It does not mean that a cause and effect relationship exists between the variables. For this, you need to use your brain. Ask yourself, does a cause and effect relationship really make sense? So in other words, something could have a, say, R value of 0.85, but in reality there's no real relationship. It's just kind of an accidental relationship. We'll talk a little bit more about this at the end of the chapter. And there's some homework questions for you, page 168, number 1 to 3.